In this video, we're going to do a few extra examples of exponential growth or decay models. So the first one we have here is, suppose we know a population of rabbits grows exponentially and it doubles every 3 weeks. If n0 is the number of rabbits initially, we want a model for n of t, the number of rabbits after 3 weeks. Okay, so grows exponentially tells us that the formula for n of t is going to look like n0 times e to the kt. Okay, so that is how we get this. So we know that's what it's going to look like. Okay, and then we know that it doubles every 3 weeks. So t is in weeks. So let's just highlight this in green. So doubles every 3 weeks tells us that n of 3 is going to be equal to 2 times n0, because that's double what it was before, the 3 weeks earlier. Okay, so we can use that to find k. Okay, so this tells us that, actually let's move over here. So this one tells us that 2n0 is going to equal n0 times e to the k times 3. And I'm going to solve for k. So we divide both sides by n0. That's going to get rid of the n0. So I have 2 is equal to e to the 3k. Now if I either take the ln of both sides or use the switching properties of the relationship between the logs and exponentials, this is going to be 3k is equal to ln of 2, which means that k is going to be 1/3 times ln of 2, or ln 2 divided by 3. Now this is approximately 0.231. Okay, so putting that in, and we don't know the initial population, so our formula is going to depend on n0. Okay, so now we know that n of t is n0 times e to the ln 2 over 3 times t. Okay, so I'm not going to use that rounded value. I'm going to use the exact value for k. But that's what our formula would look like. So then if we know n0 and we know how many weeks we want the population, we could just plug in those values. Okay, let's try a decay one. Okay, so here we have, it takes 3 years for 10% of a radioactive substance to decay. How long will it take for 80% to decay? Okay, so first of all, 10% decayed means that there's 90% left, right? So this first piece of information, okay, first of all, we know it's decaying. Okay, so we know, so let's call it A of t. So A of t is going to be A0 times e to the kt. Okay, so we know it's going to have that form. Okay, so that's the first thing we know. And then the second thing, is from this, so 3 years, 10% decays. So that means that A of 3 is going to be 90% of what it initially was. So that's going to be 0.9 times A0. Okay, so that, is the green bit. Okay, so we can use that to figure out our k. So if I just take that and I plug A of 3 is going to be 0.9 A0 is equal to A0 times e to the k times 3. So again, the A0s, if I divide both sides by A0, is going to cancel. So that's 0.9 is equal to e to the 3k. So doing our swap, that means 3k is ln of 0.9, which means that k is ln of 0.9 over 3. And if you compute that, it's a negative number, which is good because it's decaying, so we know that value is negative. So that's negative 0.03512. Okay, so we found our K. And then what we want to know how long will it take for 80% to decay. Okay, so 80% decays means 20% left over. Okay, so we want T so that A of T is equal to 0.2 times the initial amount. Okay, so that's going to be 0.2 A0 is equal to A0 times E to the ln of 0.9 divided by 3 times T. And then we want to solve for T. So again, dividing by A0 is going to cancel out that A0s. So I have 0.2 is equal to E to the ln of 0.9 over 3 times T. So using the relationship, that's going to be the exponent is equal to ln of 0.2. So then if I divide by the constant out front of the t or multiply by the reciprocal, so that's 3 over ln of 0.9, then I solve for t. So that means t is equal to 3 ln of 0.2 divided by ln of 0.9. Okay, and if you compute that, it's approximately 45.83. Okay, so it will take, so for 80%, 80% of the substance to decay, it will take approximately 45.83 years. Because T was in years there. Okay, now the last example we're going to do is one where it has a carrying capacity. So it's not uninhibited growth or decay. So that's following this logistic model. Okay, so it looks like that. I think they give us the formula though, so let's just go. So suppose a colony of meseeks live together on an island. Their population can be modeled roughly by this function P of t, okay, where P of t is the number of meseeks after t years. Okay, so it looks like that. So 12,000 divided by 1 plus 4.5 e to the minus 0.1 t. So the first part wants to know how many meseeks initially arrived on the island. So that's after 0 years. So this is going to be P of 0. So that's going to be 12,000 divided by 1 plus 4.5 e to the negative 0.1 times 0. Okay, so that's 12,000 divided by, so this bit here, this is e to the 0, which is 1. So this is going to be 1 plus 4.5, which is 5.5. Okay, so that's going to be 22,181.8. So we can't have part of a meseek, so we would probably say there were initially 2,182. Okay, now how long until over 9,000 meseeks live on the island? So that means that we want T, so that the population P of T is bigger than 9,000. Okay, so that's P of T, so 12,000 divided by 1 plus 4.5 e to the minus 0.1 t is bigger than 9,000. Okay, so what we can do is multiply by this bottom bit on both sides. Now this bottom bit we know is going to be a positive number, so I'm just going to multiply it. So that gives me 12,000 is bigger than 9,000 times 1 plus 4.5 e to the minus 0.1 t. So I'm just going to make a note here. So e to the minus 0.1 t is always positive. So this bottom bit is always positive. So I don't need to change the sign. Okay, so I know that number is positive. So I don't have to, it's in fact bigger than 1. So I don't have to worry about the sign. Okay, so now I'm going to expand the 9,000 through. So that's 12,000 is bigger than 9,000 plus 40,500 e to the minus 0.1 t. Okay, so then subtracting 9,000 on both sides. Okay, to get rid of it. So that's going to be 3,000 on this side is bigger than 40,500 e to the minus 0.1 t. So divide by 40,500. I'm going to have I think it simplifies to 2 over 27. Maybe I better not skip that step. Okay, so it's 3,000 over 40,500 is bigger than e to the minus 0.1 t. I want to double check this. So I don't want to round. So I don't want to round this number, but I can simplify. Okay, so it's 2 over 27 is bigger than e to the minus 0.1 t. Okay, so now I can use the condition, so the switch here. So that means that ln of 2 over 27 is bigger than negative 0.1 t. And now here I need to divide by the negative 0.1. So here's where I want to switch the sign. So ln of 2 over 27 divided by negative 0.1 is less than t. Okay, and if you compute that number, it's approximately 26.03 is less than t. So that means it will take more than 26 years for population to reach 9,000. Okay. Now, what is the maximum number of Mesiques that will live on the island? So this, we want to be aware. So this is in the form. Okay, so let me just say here. So P of t, I'm going to rewrite it. 12,001 plus 4.5 e to the minus 0.1 t is in the form c over 1 plus a e to the negative bt. Okay, so remember that this thing has carrying capacity equal to C, which is the maximum. Okay, so P of t is less than C for all t, which means that the maximum is going to be 12,000, the C value. So that's some examples with exponential growth and decay models.